biometrician. From 1983 to 1985, he's worked for the industry, academia, and the federal government of Canada. And he has been the head of the Center for the Resource Assessment for the Survey Methodology, Department of Fisheries and Oceans in St. John's, Newfoundland. And he then moved to the Virginia Institute of Marine Science, where he was professor in the Department of Fisheries Science until his retirement this past year. His interests lie in the interpretation of various types of data and the estimation of population parameters. And he's done extensive work on mortality estimation, design, and interpretation of tagging studies, design of fishery surveys, and creel surveys. He works with the Great Lakes Indian Fish and Wildlife Commission and the Minnesota DNR on assessment of fishery resources in Mille Lacs Lake. With that, I'll hand it over to you.
Okay.
All right.
Okay, so feel free to interrupt me during the talk if you have questions. This talk is kind of pitched to people of all levels. So some of you will just get the concepts. Some of you will grasp more of the details of how to actually implement it. Get out of it whatever you can. But I'm trying to give a perspective of, what's possible. Why can you do certain things? Why can't you? I'm actually kind of pleased with the way the talk came out, because I think it does cover a wide variety of topics. So hopefully it will be interesting to a wide suite of people. So this is me a few years ago when I was, I guess, closer to my prime. You can see that I've never been kind of a normal kind of person. And this is me now. I retired in July and they put me out to pasture, except that I keep wandering back into the barn to comment on things. Okay, so I'm afraid that to get us started, I have to define some terms so that you know exactly what I mean when I say mortality rate. So we usually talk about the total mortality rate being composed of the fishing mortality rate and the natural mortality rate. So this is the mortality due to everything except fishing. And this fishing mortality is what you're harvesting, but also what you're discarding, what you're releasing. If it dies, it gets added to this. And the way I've written it here, these are instantaneous rates. So they apply for the next second, and then you have to integrate over time to find out what's the actual annual mortality rate. So we can work in annual rates, we can work in instantaneous rates. Sometimes it's conceptually easier to think in annual rates, but oftentimes mathematically, if you do it instantaneously, here it's very simple, just add up fishing and total. And these are traditional, but they leave a lot to be desired. For example, the fishing mortality rate, well, that would include pollution and power plant impacts and so on, because it's not really natural. So the F, you sometimes want to decompose it. You might want to say, well, how much of that is American fishing and how much of that is foreign fishing? If you have, say, Lake of the Woods, it's part Canadian, part American. So who's taking too much, So you have to quantify how much of the Americans taking, how much of the Canadians taking. The reason that we think in these terms is simply that fishing mortality you can control, and it determines what benefit we get, how much yield. Natural mortality rate is generally thought of as uncontrollable. So in the past, they tried to just treat that as a constant. And since it was thought very hard to estimate, they often said, well, it's probably around 0.2. I don't know if you've seen it, but there's a cartoon. John Pope was a character, famous fisheries scientist from the Lowestoft lab. And one time he made a document that looked like an ICNAF stock assessment working sheet. And he called it ICNAF, instead of research document, he called it ICNAF dumb doc. And he showed the template, to do an assessment. You show them what's the asymptotic size, what's the von Berle growth coefficient, what's T0, what's the length weight conversion, what's the natural mortality rate, and the natural mortality they often put in a question mark. And then he showed that if you write a question mark sloppily, it looks kind of like a 0.2, and if you write it even more sloppily, it does look like a 0.2. So he said that's how we wound up with 0.2. All of which was to say there really wasn't much of a scientific basis for saying n is 0.2. But we've come a long way since then, and you can't just say 0.2. Yeah.
Just so uncontrollable, but I assume most of it's probably true. Well, my point is there might be controllable and complex elements like stocking of walleye, for instance, that are predaceous fish that would influence natural mortality, what you're calling natural mortality. So I'm wondering how it's not as simple as you're saying, I think.
I'm trying to give the origin of this. Okay, so in the past, things were very simple. That's 0.2.
Right.
Or, well, it's not 0.2, but we're not quite sure it is. It's probably around 0.2, or, well, we estimated the total mortality rate when there wasn't much fishing and it was 0.2, so it's probably a little bit less than 0.2. It was very much seat of the pants. We need an answer. Let's simplify it. Right? Fishery science is a practical science, so it's always a matter of simplifying so that we can get an answer, as opposed to saying it's so complicated that we have no answer, and then what do we do? Okay. So we also want to think about, well, what's the difference between survival rate and mortality rate? So the survival rate is the proportion of the animals present at the start of the year that are still living at the end of the year. And that's e to the minus z, where z is the instantaneous total mortality rate. So in the talk, whenever I say s, it's like, well, if I know s, I know what z is. And then whenever I say z, well, if I know z, I know s. It's just a one-to-one mapping, a simple formula. And then we also need to think about exploitation rate, which we call little u. And that's the fraction of the fish present at the start of the year that get caught. Okay. And that's kind of important to remember that it's present at the start of the year, because often during the year you get recruitment coming in. And so your total catch then is a little bit harder to interpret, because some of it is U and some of it is, well, but those are new ones coming in. But it's fraction at the start of the year that get caught, and that has this relationship with fishing mortality and the total mortality. This is written out if fishing is continuous throughout the year, and it turns out that its definition of U doesn't change much. The results don't change much if fishing is, say, only in the first half of the year, or it's in the middle of the year, or something like that. So it suffices just to work with this for this talk. If you knew more about the timing, you could do something a little bit more accurate, but it won't change the logic that I'm talking about. The key point is that exploitation depends on the fishing and the natural mortality. So if you think about 1,000 fish present at the start of the year, and there's no natural mortality, then those fish can be fished all year long. You're not losing anything. But if there's natural mortality rate going on, then the longer you wait to fish, the fewer there are out there. So because they're dying off naturally, so the fraction that you catch has got to go down. So exploitation depends upon fishing and natural mortality. Okay, so talk is about estimating mortality rates. Let's get into that. If you have an unexploited population, so your fishing mortality is 0, then the total mortality is the natural mortality, because there's no fishing. Okay, so any method that can estimate total mortality rate is giving you an estimate of natural mortality rate. So you could do a catch curve analysis. You plot log catch at age versus age, and the slope of that is the negative of the natural mortality rate. Or you could do a Brownie tagging model, and you're estimating the survival rate, but that's the natural mortality. If you convert it to instantaneous rates, it's the natural mortality. So for a long time, most of what we knew about natural mortality was, well, if we could study unexploited stocks or stocks that were lightly exploited, that would give us some idea of natural mortality. that begs the question, but what if there's natural mortality and fishing mortality going on at the same time? Well, now it's more complicated. You can get the total mortality rate pretty easily from like a catch curve or a tagging study. But now you have to apportion. Some of that is fishing and mortality, some is natural mortality. And because that was thought to be difficult, people looked for shortcuts. So Daniel Pauly, this is Daniel Pauly, was a young firebrand in the 80s, and he published a paper in 1981 and said that you could predict the natural mortality rate if you knew the von Bertalanffy growth parameters and the average water temperature that a fish stock lived in. So he regressed estimates of M that he took from the literature for unexploited stocks and on K, L infinity, and mean water temperature for, I forget how many, 181 stocks or something like that. And I say, what an outrage. He got, just hails of criticism. And he was telling me that, yeah, he went to an ICES meeting, International Council for the Exploration of the Sea, and he was presenting some of his work. And a scientist stood up and said, I work on cod. Do you mean to tell me that if I want to know about natural mortality rate of cod, I have to look at data from trout? Trout can tell me nothing about cod. And the person was just outraged that Pauly would produce something like that. So the idea of a comparative life history study or a meta-analysis, or we have all kinds of names for it nowadays, that was just outrageous. And funny thing was, a couple of years later, Pauly was at the ICES meeting, and a scientist stood up and was doing a stock assessment, and he used Pauly's M as one of the parameters. And somebody pointed out, but weren't you highly critical of Pauly's work just a few years ago? And the scientist said, well, if Pauly can do it, why can't I? So people kind of said, I don't like this, it stinks, but I don't have anything better. So, okay, I'll use it. Maybe I'll hold my nose, but I'll use it. So that has been a standard method in all the textbooks. It's been cited, I think, about 4,000 times. That was basically a basic tool. So then this is me and my wife when we were graduate students, and you can see I haven't changed much at all, except, well, I guess my hair was a little bit darker back then, but I was studying sharks, and I was impressed by the fact that dusky sharks could live 30 years. Wow, that must be telling me something about the mortality rate. I mean, it can't be high if they're living that long, can it? But I couldn't figure out, so what's the relationship? So one day I just started, plugging in numbers that I found in the literature. So on the y-axis, I put the natural mortality rate on a log scale, and on the x-axis, I put maximum age, and in fact, there's a linear relationship. Actually, I first did it without logging it, and it looked like a C. And then I thought, well, try logging it, and it straightened out. And so my crazy idea was, so if cod live about 20 years, then they probably have, somewhere in the middle there, natural mortality rate of about 0.2, which matches up with the ICNAF 0.2 that everybody was using, but also matched up with published studies of cod that said they had a natural mortality rate of 0.2, at least on George's Bank. And I had no idea, like, what do I do with this? So I showed it to my professor, and I said, he said, oh, that looks really interesting. I said, really? Do you think it might be publishable? And he said, sure it is. Oh, okay. So I submitted it to a journal, and it was rejected. So I submitted it to another journal, and it was accepted. And then it was promptly ignored for a few years. And then suddenly everybody started using it. And it became a standard technique. And in my mind, it was, if somebody says natural mortality rate is 0.8 and a species lives 25 years, should be about 0.2, 0.8. That doesn't seem reasonable. So I thought, this could kind of be like a red face test, you know, like, does this even make sense? I never thought people would actually use the regression line and say, okay, here's M, let's plug it into our model and calculate total allowable catch or something like that. But once you publish something, you lose control of it. It's in the literature and people did what they wanted to. So people started using it all over the place, which was horrifying to me. Although it was nice that I was being cited all over the place. And then for many years, people wondered, well, which is better, Pauli's method or Hoenig's method? Pauli traveled all around the world giving lectures on stock assessment methods, whereas I didn't have that opportunity. So his got cited a lot more than mine. Plus, also, it's easier to get von Bertalanffy growth parameters than it is to get maximum age. So he's got used more, but nobody knew which one's better. Like if I had growth and maximum age, which should I use? And I thought about it and said, how am I going to answer that? We don't know what's the true natural mortality rate for any stock. So for years, I was kind of blocked. I couldn't really do anything to evaluate it. And then I took on a student, Amy Fenn. She's from Malaysia, and she's now back in Malaysia as a professor. And what we did, I had Amy put together a data set of about 201 species of fish for which we had an estimate of natural mortality rate and the von Bertalanffy growth parameters and the water temperature and the maximum age. And we don't know what's the true M for any stock, but we do know what's in the literature. So we can say which method best predicts what we know about natural mortality, which method best predicts the natural mortality rate estimates in the literature. But just by looking at published says 0.37, we say 0.25, subtract, that's the difference between them. And we can sum up all those differences or square differences and see, so which one gives you a lower sum of squares, the Hoenig method or the Pauli method. And so I said, okay, this is worth doing. We can say which method works better. But we can't say how well either method actually works because we don't know what's the true end. And you'll see people in the literature saying that empirical methods are too imprecise to be useful, so don't use them. But when they're saying that, what exactly is their logic? What they're saying is, okay, here's an empirical relationship. There's a great deal of scatter about the regression line, which I didn't actually draw in this figure, okay? But when you see this point or that point or any point, it's not on the regression line. Why is that? What they're assuming is the data points are correct and the regression line is not going through all the data points, it's inadequate. But it could be that the regression line is correct and all these points are not on the regression line simply because it's hard to measure natural mortality rate. And when you measure it, there's going to be some error that pulls it off the regression line. So I argue that the regression line might be exactly right and all the discrepancies you see is just measurement error. The truth, that's an extreme position. The truth is going to be somewhere in between. The points are not on a sinful line because the line is inadequate and the data points have measurement error. So you can't see how much of it is measurement error, how much of it is inadequacy of the model. So I maintain that you can't say how well any method works. You can't conclude that they're too imprecise to be useful, but you can say the residuals from using maximum age are much smaller than the residuals from using growth parameters. And that's what Amy concluded. So she published her paper in 2015. And I have here a note, sometimes publications take on a life of their own. My 1983 paper is still being cited. It's cited something like 1,800 and something times. And every time I check, it's like, oh yeah, a few more citations for that paper. Amy's paper has about 450 citations, and it's going up over time. So I'm hoping that eventually people will catch on. The 1983 paper was good for what it tried to do, but it's out of date. Use the revised one with better data, more data, better data. But you don't necessarily have control over what people are going to do and what they're going to say in the literature. By the way, this paper from 1983 was my second paper. My first paper, I think, was a note on the occurrence of cartilage canals and shark vertebrae. And the second one was this paper on estimating mortality rates from longevity. And so for many years, it was my best cited paper. And so I like to tell people that, yeah, you know, graduate school, that's the time of your life. After that, it's all downhill. Then I did in 2001 write a different paper, a statistical paper that's actually been cited more than this one. So maybe not true that your best work is as a graduate student, but it likely is because you really slave over your dissertation and you have a whole committee that's looking over your shoulder and making suggestions. Enjoy the graduate school and see what you can produce. It may surprise you. Okay, so what Amy found was that longevity works much, much better than the growth parameters. And then the question is, well, what if we did a supermodel? What if we had longevity and growth parameters and maybe temperature or not? And it turned out that none of the models perform better than just using longevity. So knowing growth doesn't really help you to get a better estimate. Of course, if you don't know longevity, then by all means use growth, because then you can get an estimate. But if you have longevity, it's probably the best thing to use. And that was very disappointing to me because I was kind of hoping that with two different methods, if one of them was screwy, you'd at least have some indication that somewhere something is wrong, because look how far apart these estimates are. But no, the growth parameter estimates don't really work that well. So,
You know,
sure.
does anyone look at domesticated fish to see to what extent this is an intrinsic property of the organism, the mortality, the age, or is it something more complex related to the like what's talking
Kyle Lorenzen at Florida State, no, University of Florida, has done some work with aquaculture fish, but I'm not really up on the details of what he was doing. He was trying to get natural mortality rate as a function of age or size.
I've been wondering this for invasive fish, see? when they're-
Not really. That's kind of, everybody wants to push things further. They want to know, how does natural mortality rate vary by age, by space, by time? And there are efforts to build that into stock assessment models, but it's asking an awful lot of a parameter that traditionally was considered too hard to estimate. So then a lot of people have said, well, but does taxonomy matter? So, you know, I have this relationship for natural mortality as a function of longevity. But if I knew that it's a shark or it's a salmonid or a centrarchid, would that tell me more like, oh, then the relationship should be shifted? So Beth Babcock at University of Miami asked for the data Amy had compiled, and she fit a hierarchical Bayesian model with family being a random effect. So you have your estimate of I for stock I is equal to an intercept that depends on the family that stock I is in. G of I says, what family is stock I in? So this coefficient depends on the family, and then a variable, growth, longevity, maximum size, longevity, von Berland, PK, whatever, for the ith stock in family J. raised to some coefficient that depends on the family. Sorry, variable J, stock I, variable J, and this coefficient that depends on the family with an error. And if that looks intimidating, just think, well, what if I take logarithms? So I'm saying, well, the log of n is going to be equal to an intercept that depends on the family plus, and this is just a linear relationship, beta times an environmental variable. So beta times water temperature, beta times von Bertalanffy K, beta times asymptotic size. But the beta is different for each variable. Okay. So what she found, well, first of all, what does this do? It's really doing a compromise between pulling all of the data, just saying, here are all my data, let me do one regression line, ignoring the family, or doing a separate regression for each family. Now, doing a separate regression for each family is nice because it gives you family-specific relationships, right? It's bad because I might have 200 data points, but for the family I'm interested in, I only have 12 data points. So now I'm doing a regression based on 12 data points. That's not going to be very precise. So what this hierarchical Bayesian does is it compromises. And it says if the data are good for a family, it'll let the data for that family speak for itself. But if the data are not good for the family, like I only have 4 data points for this family, then it will shrink it. It will pull it in towards the average. So it does allow, compelling data to say, no, this is different from everything else. But if you don't have a compelling case to say it's clearly different from everything else, then it says, all right, so it's really the best I can do is what's the average. Okay. And okay, so that's what it's doing. And so these are predictions for an average fish in each studied family, restricted to those families for which we have at least 3 data points to do the regression line. And on the top is based on Tmax. And you can see that the predictions aren't really varying very much by family. So family doesn't seem to be changing the relationship. But for growth, that is to say, when I'm predicting natural mortality rate based on growth and temperature, oh, yeah, different families need different relationships. So this is a very small fish. This is sharks, and so on. So the question we were asking is, does taxonomy matter? Not really when you're trying to predict natural mortality based on maximum age, but yes, it matters if you're trying to do it based on growth parameters, because growth parameters by themselves don't tell you the whole story. Different families have different biology. I'm quite excited about this, and I'm trying to kick Beth to finish it up so we can get it published. Oh, the other thing is that when you look at the credibility intervals, which basically says, how reliable is this estimate? They're tighter when you're using maximum age than when you're using growth parameters. And also with this hierarchical approach, it only really helps you if you want to predict M for a family that's been studied. But if I say, well, here's a family, it's not in my database, what's my prediction? It uses the average line. It doesn't have anything to say, oh, this family is going to be lower than most other families. Final point is the results are somewhat unstable, especially for families where you only have 3 or 4 observations, which means that over time, we'll get more estimates of natural mortality. We can update the database and our estimates will change. And that's a little bit unsettling that you do an assessment. You say, okay, here's our best guess as to what's going on. And here's what we think is the sustainable yield and what our quota is going to be. But then a year or 2 later, you say, well, actually, given what we now know, if we revise it, the M was too high and should be brought down, or the M was too low and should be brought up. So You just have to be aware of the fact that, yeah, this is not the end of the story. It'd be kind of nice if you could, pi is 3.14158, as many decimal places as I want. And 10 years from now, they're not going to say, well, Hoenig was using 3.1458, but we all know that it's really 3 point whatever, something else. Yeah.
How often was it the case that the credible interval for the T-max version of this fell outside of the range that you would have gotten had you not used the Bayesian approach, the hierarchical approach at all? You know what I mean? How often was it that a family's Bayesian estimate for the credible interval was different from the original version that didn't consider family?
Okay. It's a fair question. You basically asked me to get into more details than I wanted to for this talk.
I can ask you that.
They were very similar, and that was my point. But if you actually were to read the manuscript, you'd find out that for the T-max version, whether family was important depended in part upon which criterion you used. So if you use BIC, you say it's not important, but there are other methods of assessing results, and some of them said family is important, some of them said family isn't. So we looked at it and said, all in all, it doesn't seem compelling that, yeah, you should be making sure you're considering family. Okay, so those are the, back in the day, we used to call them quick and dirty methods for getting natural mortality rate. Now we call it data limited methods or data poor methods or something like that. It's come up in the world a little bit. But what if we actually want to design a study to estimate natural mortality rate? So generally, if fishing mortality is not zero, then the strategy is to estimate two functions of fishing and natural mortality. So one is if you can estimate the total mortality rate from, say, a catch curve, you would say, okay, I've done my catch curve, Z is 0.5, and that's estimating F plus N, but I don't know what F and N is. And then if you estimated the exploitation rate, U, that's catch divided by starting abundance. And you could estimate this, for example, if you tagged 1,000 fish and you had people at all landing points to see all the fish coming back in, and you saw 300 fish were caught out of 1,000 tagged. So that's estimating that 30% of the fish were caught. That's the exploitation. So I might have, as an estimate, exploitation rate is 0.3, and it's a function of fishing and natural mortality. So now I have two equations in two unknowns, and paper and pencil, you don't even need a calculator. You can say, oh, so I estimate the natural mortality rate is 0.12. Okay. So that's the general strategy for estimating natural mortality rate. So what bothered me was that there was really no guidance as to, well, how do I design a study to estimate natural mortality? I got money, I want to do this, what am I going to do? So I was working over the year, the 20-year period, with Bill Hearn from Australia, Ken Pollock from North Carolina, Rob Latour, who was Ken's student and then came to VIMS, and George Lee in Australia. And what we realized is, first of all, you almost always need contrast in fishing mortality if you want to estimate natural mortality rate. Did I go wrong direction? I did. So this slide, so I was at a workshop in Rome in November on best practices for stock assessment. And I was trying to say you need contrast. And I said, you know, what people are doing nowadays is they're doing these integrated models where they throw everything but the kitchen sink into one model, and they expect that it will tell them fishing mortality. And I said, could you estimate M from an integrated model if fishing mortality is constant? It's just one number, one fishing mortality. And the answer is no, you can't. You won't be able to separate fishing from the natural mortality. Unless it's one of these special cases. So what are those special cases? Where don't you need contrast? Tagging studies with tag reporting rate known, because if you know the tag reporting rate, then you know how many tagged fish are caught, and if you divide that by the number of fish you tagged, you're getting U. So then you have U, and if you can get the total mortality rate, you can from a catch curve data collected in 1 year, you could estimate FNM even though you don't have any contrast. Or studies where N is known or it's estimable. For example, in some telemetry studies, you tagged N fish and you're observing them, and you can tell when each one died of natural causes and when it was caught. And so, all right, in 1 year, you could say how many died of natural causes. So then you wouldn't need to have contrast. Or here we have close kin analysis with catch known. Okay, now you're getting estimate of population size. So total catch divided by population size is exploitation rate. That's your second equation for, and you can also get mortality rate from that. Or a survey, if your survey year efficiency is known. So supposing you know that if I drag this trawl across the bottom, I will cover 0.1 square kilometers, and half of what encounters the trawl will get caught, half will escape. Well, then you could just do a swept area calculation and say, I know how much was in this 0.1 square kilometer, and I know how big the lake is, so multiply it out and you get your population size. Okay, well then you can get catch divided by population size is exploitation. And if you have, say, a catch curve to do total mortality rate in 1 year, you're getting your answer. So these special cases, studies where N is known or estimable, or studies where the tag reporting rate is known, then you don't need contrast. Otherwise, you have to have it. Okay, so I'm saying you need contrast in fishing mortality. I'm not really saying what I'm sure what I mean by that. Fishing mortality could vary over time. And by that, I mean from year to year or within a year. It could vary over age or size, or it could vary over space. How am I doing for time?
It's 12:40.
Okay.
I'm gonna plug in my laptop, so it doesn't die.
Okay. So it has to vary. And if the fishing mortality has to vary, then you can design to have contrast in your data. So I'll give you some examples. Here's contrast among years. Supposing at the start of each year, you do a survey, or if you prefer, you could tag a bunch of animals. Then you have some catch over the year, and then you have a survey, and then you have catch, and then you have a survey, and so on. And so this is year 1, year 2, year 3, and note that the abundance is going down over time. The height is going down, and the exploitation is going up. This is that high, that higher, so more being caught. Okay, so the survey ratios. So this divided by this. This is an index of abundance, proportional to abundance. So QN, Q is a proportionality factor, N is the abundance in year 2, divided by QN in year 1. The Q's cancel out, so you have N2 over N1. That is the survival rate. Okay, and the catch divided by the survey index is proportional to the exploitation rate. Basically, this is catch divided by the abundance times Q, that nuisance parameter, that catchability. Okay, so if you do that here and here, Okay, the survey ratios are giving you S1 and S2, or equivalently Z1 and Z2. Those are functions of F1 and M and F2 and M. And the catch over the survey is giving catch over Q times N. Survey is proportional to abundance. So catch over QN is giving you exploitation rate in year 1 divided by Q, and exploitation rate in year 2 divided by Q, which are functions of Q and F1 and M, and Q and F2 and M. So while it seemed kind of complicated, which is my point, so you wind up with 4 equations and 4 unknowns. Z1, which we measure, is F1 plus M. Z2, which we measure, is F2 plus M. Catch over survey in year 1 is U1 over Q, which is a function of these things, and catch over survey abundance in year 2, which is other function. So 1, 2, 3, 4 equations with 4 unknowns, Q, F1, F2, and M. So you can solve those simultaneously. Ugh. Very inefficient, so it's not going to be very precise, but you could do it. Note that if the fishing mortality doesn't change, the natural mortality rate doesn't change from year to year, then this is just a replicate observation of that. It's no new information. It's just more information on what's Z1 equals F1 plus M, because this is the same as that Z. So then it won't work. Okay, so you need that contrast. Here I say instead of surveys, you could use tagging and then use a Brownian model to get Z1 and Z2. So I'm trying to say that this is a general process, not just a specific case. And as I said, if fishing is the same each year, then you just have redundant observations instead of different observations. Okay, now this is contrast within years. So you have a survey, some harvest, a survey, period with no fishing, and then the next year, the same thing, survey, harvest, survey, period with no fishing, and so on. Now, these survey ratios are giving you, well, these survey ones are dependent on the catch survey ratio is just measuring natural mortality, right? This survey would be the same as that survey if nothing died, but you see less here than you see here, measuring the natural mortality rate. And I hope it's understood that when I say this survey, it's not like, oh, I got 20 fish per gillnet lift. This would be 20 fish age 3 and above, 20 fish age 3 and above. In the previous slide, when I was comparing beginning of the year and beginning of the year would be 20 fish 3 and above, 15 fish age 4 and above, so that these are the survivors of these. But here it's within a year, so 3 and above, 3 and above. That's telling you the natural mortality rate. Or you could use Hearn, Pollux, and Brooks to have a tag before and after model. These are giving you direct estimates of natural mortality rate. So it's much more efficient than the previous one because I'm using the within year contrast in fishing mortality. Okay, so note the design implication. You need to isolate, or in other words, monitor the contrast. So that means you have to have surveys before and after the fishing so you can see what's happening. Or you could do it with tagging before and after. Also, generalization, you don't have to have a closed season. You could say most of the fishing is in the summer, some of it is in the winter. The fishing mortality in the winter is less than the fishing mortality in the summer, and this approach would still work. And another generalization, you have to isolate the contrast. So if you recorded effort by period of the year as an alternative to doing the surveys to get the relative abundance, if you assume that the fishing mortality is proportional to the effort, you could also build a model. So that was contrast with time. Fishing mortality is not constant over time. It allows you to do this. Hope I haven't gone too fast. You following what I'm saying, that you basically need to say, here's what's going on when there's high fishing. Here's what's going on when there's low fishing. That's giving me a way of saying, you know, the total mortality going down, but it's going down because, not because M went down, but because fishing went down. And that allows you to separate out what's the impact of the fishing, what's the impact of the natural mortality. You could also do contrast by age or size. So I did a paper with Rob Latour where we suggested tagging lobsters 1 molt away from legal size and also tagging legal sized animals. So the legal sized animals are experiencing fishing and natural mortality, and you can get their survival rate. And then the ones that are 1 molt away from legal size, they're big animals, they're almost legal size, so they should have similar natural mortality rate, except for the fact that they're slightly smaller, but they're not having fishing mortality. So now you have a way of saying, I've got 2 different mortality rates with different fishing mortality, so I can solve for fishing and natural mortality. The other thing is you could tag various ages and estimate selectivity from short-term tag returns. And this paper here actually was done with the Minnesota DNR and the Great Lakes Indian Fish and Wildlife Commission. Is estimating the selectivity of angling for walleye in Wisconsin and Minnesota lakes. So the idea is this: say I tag animals in each of several size groups. Tag 100 animals, say tag 100 animals in each size group, and then I look at the tag returns, and I see 3% back from the first group, 3% from the second, 3% from the third, fourth, fifth, sixth size, all the size groups, I'm getting back 3%. That implies there's no selectivity. All sizes are equally vulnerable. But if I saw, okay, the smallest animals, I'm only getting back 1%, and then the bigger ones, I'm getting 2%, and then 3%, 3%, 3%, 2%, 1%. It's saying my gear is good at catching middle-sized animals, but it's not catching the small ones and the big ones. So that's your selectivity curve right there. All you have to do is scale those ratios, those percentages, to have a maximum of 1. If you do that, then you basically can apportion the fishing mortality among ages to get contrast. So you're getting your fishing and natural mortality. Again, if you don't follow the details of it, try to just follow the logic that it's the contrast that's allowing you to separate them. Okay, the third design general principle is that the model must express contrast explicitly. You have to isolate that contrast. So say you have catch data by month of the year, but you pool it over the year. Okay, you now have obliterated, you're losing the within year contrast in fishing mortality. All you have is 1 number for the year, and you can't say, oh, but you know, later in the year, this is what happened. And there's a principle of parsimony that you may have heard of that says, you know, pick the simplest model that will get the job done. So people would say, why would I want to estimate what's going on, you know, each month of the year or each period of the year? That's just going to make my parameter estimates less precise. And it's true that if you don't care about these extra parameters, like what is going on in each period of the year, then parsimony says collapse the data and get more precision for the parameters you care about. But if what you care about is, say, third quarter of the year for some reason, then obviously you can't just lump it in with the whole year because you lose that information. And if what you care about is natural mortality, then don't do this knee jerk, I'll just summarize everything by year. And when you see the integrated models that people are doing, they often will just take annual catch data and don't you have it by period of the year? Oh, yeah, but you know, that's more computation, more busy work. It's like, unless it will tell you something important. So the principle is that you need to make sure that you express that contrast explicitly. And then people want to ask, yeah, but what if M varies by age? So they want to get more detail. Like before, people were saying we can't even estimate natural mortality and we have to use a comparative life history study. And now when you say, well, you can estimate natural mortality, they're immediately saying, yeah, but I want to know it by age. So the same principles apply. You could estimate M separately for each age. And then you have to get contrast, but you could do that from variation in space and time. Or you could design to use the fact that M is varying by age. And what you have to do is estimate the selectivity like through a tagging study. And now you have contrast with age, but you know how it's responding to age. You've got your selectivity. Then it becomes quite easy from one study to get M by age. But you have to design for that. You have to say, yeah, I need to know the selectivity, because if I try to estimate the selectivity, it's going to be confounded with selectivity by age and natural mortality by age. How do you separate those two out? Well, you can separate them out if you know the selectivity, then the rest is natural mortality. So what I've tried to say is that natural mortality can vary by time, age, or space. Generally, you need some assumptions about what's constant, or you need additional information. You need to know your gear selectivity or your gear catchability, or else you have to assume that it doesn't vary by size or whatever. If you have contrast from multiple sources, that would allow you to test some of your assumptions, because you could say, I'll use the variation in fishing mortality with time, estimate M, but then I'll use the variation in fishing mortality with age, and I'll get the estimation. If they agree, great, everything seems fine. If they disagree, you have some diagnostic. Okay, last thing, I'm going to switch topics a bit. What if natural mortality changes, say due to an emergent disease? So in my work, I've worked on snow crabs, and these are normal snow crabs. But these have bit of crab disease. These are normal, the underside. Sorry, I have to step back to see which. Okay. The reddish ones have bitter crab disease. The brownish ones are normal. The bleached looking ones have bitter crab disease. The normal ones are kind of dingy. This just showed up in Newfoundland, Canada, 1 year. This is striped bass with mycobacteriosis, so it has all these ugly lesions. And this is an American lobster with epizootic shell disease that showed up in 1997. Just showed up, it's been expanding. The parapet should look like this, nice and smooth, but it's got all this pitting in it. And actually, if you were to take your finger and do that and break through the shell, normally very hard, but this is brittle. So the question is, should we care? Should we be alarmed? Normally, the approach is, well, let's find out what's the causative agent. So study the etiology of it, the mode of transmission, ecology, and all of that. And I said, why don't we do it backwards? Why don't we first see if this matters? If it matters, then we need to know all this other information. But if it's not causing any mortality, then who cares? And then it's not worth $1 million of funding on an emergency basis. So that's what I'm saying here. It's expensive to do all these background studies, but we could determine the impact of the disease before, just by doing a tagging study. So in a tagging study, a cohort of animals and not declines exponentially to give you the number at time t. And if you look at the ratio of healthy to diseased animals, it's equal to the initial number when you do the initial ratio when you do the tagging, and then the healthy ones decline according to this disease, the diseased ones decline according to this disease. So what you're getting is the initial ratio times something that depends on the difference in mortality rates. If you take the logarithm of that, you're saying the log of the ratio over time will evolve, and it's equal to the log of the initial ratio plus the difference in mortality rates times t. So the slope of this linear relationship is the difference in mortality rates. And actually, if you exponentiate that slope, you're getting the ratio of the survival rates, which maybe is a little more intuitive. And what we found was with snow crabs, if they're diseased, they have about 1% of the survival rate of non-diseased animals. So this method doesn't tell you what the survival rate is. It tells you the relative survival. Whatever the survival rate of non-diseased animals is, these ones have 1% of that survival rate. And it's interesting that the spitter crab disease in Newfoundland, it's episodic, meaning some years, most years it's low, and then you'll find a year where, oh, it's 20% or 50 of the animals have it. So like when you see it, yeah, those animals are going to die. For striped bass, animals with moderate disease, so just some of the blotches, have 84% of the survival of undiseased animals, and the prevalence at the time of the study was about 15%. And severe disease, about 11% of the animals have really ugly sores, and their survival was about half that of undiseased animals. So if you combine those, weighting them by prevalence, it seems like it basically doubled the natural mortality rate of striped bass in Chesapeake Bay. And for lobster, moderately diseased animals and severely diseased ones seem to have about 30% of the survival of non-diseased ones. So that's a third of it. Mild ones had half the survival of disease of non-diseased animals. So disease can be important when prevalence becomes high, and assessing disease mortality could be used to set priorities. Is this where I want to put my money? Is this an ecological problem of concern? And then the last thing, the management implications. In classic theory, high natural mortality rate implies that you should fish them before they die out. So it calls for higher fishing mortality to be optimal, ignoring whether that would cause recruitment problems. But just from a yield perspective, assuming that recruitment is not affected, high natural mortality implies that you can have higher fishing mortality. And some people, like Steve Cadron at University of Massachusetts, argue that if you have an increase in M, you can increase the fishing mortality. I argue that stock is not adapted to higher M, so this additional mortality is additional stress. So you should increase it. So you should increase your value of M in your assessment by the amount of disease mortality, not by sorry, I'm messing with the increase in M should be accommodated by reducing F. So if your F is, you think F is 0.2, but you know that the disease mortality is 1, you should say, oh, actually my effective F, my effective stress on the system is 0.3. So reduce F if natural mortality goes up. Now, I'm oversimplifying things to make a point. Steve Cadron is not a fool. He's a friend of mine, and he's a very sharp guy. And what he's thinking is, if, for example, you have a population that has evolved to experience natural mortality, fishing temperatures between 15 and 20 degrees, right? And now what you're seeing is it's repeatedly 20 degrees. He would say, okay, natural mortality rate may have gone up, but that's not any concern. It's adapted to that. Whereas I was thinking about emergent disease. We've never seen this before. So I have no reason to think that the stock is adapted to this. And so this must be additional stress that it's not prepared to handle. So that's my way of thinking. And his is, well, the increase in M is natural. And that's the whole question. Is it natural or is it artificial? You know, we introduced a pathogen by stocking or through whatever. And each case will be different. Each case will have to be decided. And that's it. That's my talk. Thank you. That's me with my second to last student. We're down in Alabama doing some field work, and that's a nice red drum. I can't see the black spot on it. That would be a dead giveaway. Do we have time for questions?
Yeah, here, I'll gonna pull it up, this up here and see if there's any online as well, so. But yeah, if any of you have questions, go ahead. Maya's got one right there for you.
So I guess you just talked about it a little bit at the end, like it really is introduced or natural. So things like pollution, climate change, increase in water temperatures, would you consider that part of natural mortality, or so are we seeing an increase in M over time theoretically because of that?
We're likely seeing an increase in N. And my last point was, is that increase in N natural or unnatural?
Right.
Right. So pollution, I would say, is unnatural. The stock has not evolved to experience that. Increase in temperature, it depends how much increase in temperature. So if stock is adapted to experience 15 to 20 degrees, and throughout my career, the temperature has been around 17, but now it's 20. I would argue that Hadrian is right, that that's still in the normal range, and may have gone up a bit, but it's adapted to handle that. Okay. But if it then went up to 22, 23, I would argue, whoa, it's never experienced that before. That's not natural. That's new. It may not be adapted to that. That can cause stress, and you should. And so I would flip from saying, yeah, just increase M, and therefore you can increase F, to saying, whoa, we have an increase in M. We should subtract that from the F that we allow. Okay. So that opens up, lots of room for argument.
Yeah.
Because, like, well, what's natural?
So you propose decreasing.
If the increase in natural mortality is unnatural, the stock's not prepared to, is not adapted to deal with it, then I would say that implies reduce your fishing mortality.
Yeah, so I mean, the mortality based on that's when it just makes sense, right? You need to think about it. But have you sort of looked at trying to look at mortality versus age fitting in that? So in other words, is it always constant? So basically you're assuming it's constant over at least the recruited population, right? So has anybody really looked at the relationship sort of by age to see whether there's a change or inflection or something here, natural mortality?
Yeah, Kyle Lorenz, University of Florida, did that. He published a paper, and the stock assessment world was so eager to let M vary with age that they wanted to adopt that, except that it didn't quite make sense. So what they did was really awkward. They said, let's take the shape of his curve, which we like, but let's anchor it so that it, for oldest age, he has natural mortality going down with age, and I can go ahead. Age M. That's what Hoenig is. It says, if there's a certain age, all ages have that out, okay? Lorenz's curve does something like this. Huh? And they said, that doesn't make sense, that's too high. So they said, let's just take this and pull it down. So it does that. So they use Lorenz's curve, rescaled so that it'll agree with Hoenig's curve. To me, that's fantasy, okay, but they want an answer. They say, it doesn't make sense to say that M is constant for all ages. So we like the idea that Lorenzen tried to estimate it. It doesn't really make sense. So let's just make it make sense. Whether that's right or not.
So is it fair though, partly to ask of that is, with all of your data, you're really looking at recruited fish. And you're not, you don't know anything about mortality of non-recruited fish.
Right. So that's right. In my entire career, I did one paper on recruitment of tiny fish, large, shad in the Connecticut River. And there, what I did was same idea. Like, I can't really estimate the mortality rate, but I can estimate relative mortality rate. So I wanted to know if early spawned shad have a different survival from later spawn. So I looked at the ratio of numbers of cohort born in 2 divided by cohort born in week 1, and so follow that over time. And a cohort born in week 3 divided by cohort born in year in week 2, and decline. And in most cases, I can't remember now whether the earlier ones survive better than the later survive better than earlier. That's a detail. So I'm interested in methods, not in answers. Right? But it was pretty clear that in 1 year, I'll say the earlier ones always survive better, and in the other year, the earlier ones mostly survive better, except towards the end of the season, the later ones survive better. And I thought that makes sense that you don't get earlier is better than later, because if that were the case, that earlier is always better than later, everything is spawned earlier, right? It has to be that sometimes it's better to spawn later, so they hedge their bets. And so I was pleased with the results. And we published it, and it was kind of ignored for a number of years, and then it started to get noticed, and it's been cited about 30 times. So I don't know how much impact it's actually had, but it was a thought that, yeah, instead of focusing on estimating mortality rates, sometimes it's just easier and maybe sufficient to estimate relative survival rates. That's one of my pet, ideas of my career. I published that in a number of contexts, and I'm going to talk about mortality rates today. Yeah, I got to talk about relative survival rates too. Can also do the same thing with discard mortality. If you note the condition of a fish and then tag it and release it. So, okay, I caught this fish on hook and line. It seemed half dead. When I released it, it floated on the surface for a minute and then slowly kind of sank, but it swam off. And then say, okay, that's condition 3. And here's another fish, and I tagged it, and it just took off like a bat out of hell. Okay, so I don't see any stress. That's condition 1, and then you can define other conditions. And then you look at the ratio of tag retrievers that come back. And if you get that 5% of my condition 1 fish and 5% of my condition 3 fish, I guess they survive the same. But if the condition 3 fish, I only got back half as many, and you had 50% of the survival of a condition 1 fish. So it's relative. And then if you make the assumption that anything in condition 1 probably had the normal natural mortality, now you actually have absolute numbers, but you can certainly get the relative numbers, minimal assumption, and absolute survival is needed a stronger assumption. Yeah, condition when fish are surviving normally. That we did with sharks in the Gulf of Mexico, but it's been picked up now and used for a lot of different things. It's been cited like 20 times, so yeah, it finally got noticed.
So when I was old enough for grad school with Ken Pollock back in the day and everything else, and there was a lot of attention, as you rightly given to what's the sort of contrast, what sort of information do you need to be able to estimate parameters, and a lot of attention there. And as you allude to, there's a lot more now of let's do more and more complicated models with more and more parameters, much more flexibility, use Bayesian inference and priors and things that may take a long time to fit. And hard to know, do you have the contrast to actually estimate those things? So I appreciate that, you touched on that a little bit. I'm curious what you think will be happening in 15 years. Do you think there's going to be a movement away from sort of this trend, or do you think we'll have better data and a better understanding of how complex models work and be able to use those tools? Just where do you see things going?
Okay, so the first thing is that my brain is kind of small, so I have a hard time understanding complex models. So I don't like them. To me, there's so much going on that to actually know what I think about this example, this model, it's like I want to take it apart and see, which pieces are in conflict with other pieces, and why am I getting this, and what's the influence of the priors, and all of that. So I don't like that. But that is the trend, and it's driven by Rick McNaught in the National Marine Fishery Service and a coterie of colleagues that they think this is the state of the art, and it is. It's basically saying let's think about what each piece of information, kind of data, can contribute. But you'd be surprised, but the majority of marine fish stocks in the United States are managed based on their ORC stocks, only reliable catch. So all you have is like, here's how much was caught over the last 15 years. What should the quota be for next year? It's like, well, if they're catching more and more over time, that could mean that the abundance is going up and up. Or the abundance could be constant or going down and down, and they're just fishing harder and harder and driving it down, right? So only reliable catch, if that's what you have, is not a logical basis for setting a cap. That's what's done for many, many, many stocks, right? Other stocks they have more information, but they're still what they call data limited or data poor, right? And so since that's the bulk of the fishery resource, in my mind, the rational thing to do is put the bulk of your money into developing methods for data limited stocks, right? But that's in complete contrast to what we should be doing is perfecting the most sophisticated models and trying to drag everything along, like, well, all of these ORC stocks, we should make data poor by collecting more information. And all the data poor, we should make data rich by collecting more information, so that ultimately everybody can use an integrated model. So that's what's going to happen for the next few years, I think, is this emphasis on the data rich models. But in 15 years, I don't know what's going to happen, but to me, the logical thing is to say, no, most stocks have very poor information, so we should not be devising models that says, if I knew everything, I could throw it into this model. We should be saying, I only know this and this and that, so what model can I use for that? And so what I've done in my career is more data limited than data rich. And to me, a place like Minnesota, where it's not 10,000 lakes, I mean, maybe 10,000 lakes, but there are 10,000 lakes with fish, more like 3,000 or whatever. But with so many lakes, you can't do a sophisticated data hungry model for every lake. It's not going to happen. So yeah, okay, most lakes are going to be data poor. So what's an appropriate approach for data poor?
All right, any other questions?
A lot of questions.
And I don't have anything in the chat, so you're all good on that end.
Okay.
All right, well, we'll give John a round of applause.
Thank you for inviting me. Special thanks to Lynn. Kind of nice to come back here. I've been coming to Minnesota almost every year for the Mille Lacs meetings, but somehow I just didn't make it over to the university, mainly because when I'm done with the meeting, I want to get home.